structurally, this amino acid consists of 4 groups: a carboxyl group, an amino group. Are you with me?
Yes, sir. Sir.
So, structurally speaking, amino acid consists of 4 groups. We have an amino group, we have a carboxyl group, and we have a hydrogen atom. And then the last one, we have an R group, what we call R group, or a side chain. So basically, all the amino acids have similar carboxyl group, amino group, and the hydrogen atom. What makes them differ from each other is what we call the R group or the side chain. The side chain differs in structure, causes the difference in size, causes the difference in electric charge, and that determines also a distinct physicochemical properties or chemical property of an amino acid. So a chemical or physical property of an amino acid differ just because of the difference in R group. Because otherwise, removing the R group, all amino acids are the same structural. So of course you can note to see any difference in all. They can even be given one name. But because the R group differ, so you have a different amino acid with a different physicochemical properties. Is that clear? Is that clear?
Yes, sir.
Yes, sir.
Okay, so all these 3 groups, all these 4 groups, from the structure here, we can see that all the 4 groups were attached to a carbon. And this carbon is called alpha carbon. It is called what? Alpha carbon. That is in the name of, in the naming involving the use of alphabet. While there is another naming which uses number. Carboxyl group is considered carbon 1. I don't know. Can you see my cursor?
Yes, sir.
Yes, we have this carbon, the carboxyl group is considered carbon 1, while the alpha carbon is considered carbon 2. Is that clear? So the subsequent naming of the atoms continue with the carbon atom in the R group. But remember, we said this R group differs. Let's take a typical example. This next one, next structure after this is the structure of one of the amino acids. We get to know what amino acid is that when we reach there, discussing about the structure of each amino acid and their side chain. You will tell me which amino acid is it. So this amino acid with a long chain. We can see carbon 1. Don't worry with the arrangement of the structure, but I want to believe you can still see carbon 1, the carboxyl group, the amino group, the hydrogen, and then the R group. Can you identify from the structure here?
Yes, sir.
Good. So when we look at that alpha carbon, we said it is carbon 2, right? Now, carbon 3 is from the R group. So carbon 3, 4, 5, 6, and then the last amino group is specific for this amino acid. Some amino acid may have a different thing completely. But what am I trying to explain here? What I'm trying to explain is the numbering. The carboxyl group, in terms of numbering, is considered carbon 1. Then the alpha carbon, which all the amino acids have it, is considered carbon 2, and also alpha carbon. And then any other carbon attached to the alpha carbon will be carbon 3 or beta carbon, carbon 4 or gamma carbon, carbon 5 or lambda carbon, carbon 6 or epsilon carbon. Is that clear? Is that clear?
Yes, sir. Yes, sir.
So this is basically the numbering of the amino acids. Okay, now the 20 amino acids. We have 20 amino acids that exist in a protein. That does not mean that we only have thymine. Helen. 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 Can you mute yourself, Helen?
Yeah.
Okay. So we say we have more than 20 amino acids, but the most common one that are found in proteins are 20. So only these 20, either each in their natural form or in modified form, are what's found in a protein. These 20 amino acids can, in some cases, be modified and still found in a protein. Some example of this include hydroxyproline, which is found in collagen fiber. We have hydroxylysine also, is something in collagen fiber. We have gamma carboxyglutamate in prothrombin, which is involved in blood clotting, etc. You can see a lot of examples of modified amino acids that are found in proteins. So basically, these are the amino acids, starting with alanine down to valine. And we have a 3-letter abbreviation for each amino acid and also 1-letter symbol. 1-letter symbol, mostly we use a 1-letter symbol when we are trying to give the peptide sequence instead of drawing the structure of the amino acids when you want to give the sequence of the peptide. You rather give the sequence of these letters to serve as the amino acid sequence. Is that clear? Is that clear?
Yes, sir.
And remember, we said that each of these amino acids differ in terms of their R group, the side chain. And we said the side chain determines the overall size, shape, stage, the hydrogen bonding capacity, and the chemical reactivity of an amino acid, as well as the protein, the compositions of these amino acids, and the compositions and the nature of their R group determine also the function of the protein, determine also how the protein is going to be folded to form the functional conformation of the protein, which we will see in the next class. Now, before that, we talk about isomerism with regard to carbohydrates. If you can remember, we talked about D and L isomer. The same thing here. When you look at the structure of the carbohydrates or even the protein, what was the reason we mentioned that an atom could actually confer or have that isomeric form. We made mention of the presence of what we call asymmetric carbon, right? What is asymmetric carbon? Can somebody help me? What is an asymmetric carbon? Klaus?
Hello, sir.
Yes, Moses, go ahead.
Yes, sir. An asymmetric carbon is a carbon atom in an organic compound that is bonded to 4 different atoms.
Good, Moses. So that's basically a asymmetric carbon, and we call it also a chiral carbon, right? So once a compound have this carbon, the arrangement of these atoms around the carbon can actually change. So if you have a compound with that carbon, only one, then that compound can have 2 raised to the power of 1 isomer. Remember, we gave the formula about the isomer is equal to 2 raised to the power of n. The n is the number of the asymmetric carbon. If it is 1, then 2 raised to the power of 1, you have a 2. If it is 2, you have 2 raised to the power of 2, you have 4. So if a compound that have 4 asymmetric, 2 asymmetric center, then it is likely going to have 4 different isomers. So when we look at the structure of amino acid, we made mention that the 4 groups were all attached to an alpha carbon. And when you look at the 4 groups actually differ. Then that carbon is a chiral carbon. And that carbon can have an arrangement around the center to produce 2 different isomers. These isomers were called enantiomers. They were called enantiomers, if you can remember our discussion about carbohydrate chemistry. Here, I gave an example of an amino acid, alanine, with an R group as CH3. And I gave an example of, I added glyceraldehyde, which we used to explain in the case of carbohydrate. And we mentioned that in the case of glyceraldehyde, when you have the OH group to the left, it is called L-glyceraldehyde. When you have the OH group to the right, it is called D-glyceraldehyde. While in the case of amino acid, we said when we have the position of the amino group to the left, it is called L-amino acid. In this case, it is L-alanine because the amino acid is alanine. And then if you have the amino group position to the right, it is called D-amino acid. In this case, we have D-alanine. There is only one amino acid that does not have this D and L combination. Which amino acid is that? The amino acid is glycine. Glycine is the simplest amino acid. And why doesn't have the chiral center is because the R group is hydrogen. So when you have hydrogen, remember there is already hydrogen attached to carbon. So you have at least 2 of these groups that are similar. Therefore, the carbon is not asymmetric carbon. Another property we also mentioned here is the optical activity. Optical activity. We said whenever we have a compound that contains this chiral center, it used to have optical activity. That the solution of this compound is optically active in the sense that we can rotate a plane polarized light. So when you fast a light into a solution containing this amino acid, it can rotate the amino acids. So if it rotates left, it is called laboratory. If it is called, it's rotates right, it is called exploratory. So in that respect, we also have L and you know how we presented it in the case of carbohydrate, where we can have D positive and D negative. And we say positive, it is dextro, and negative, it is label. So it can be, like we said, L class aldehyde can be L positive, meaning L, but laboratory, or L dextrorotate. D laboratory, or D dextrorotate. Is that clear? So the same thing in the case of amino acid, we can have D isomer and the L isomer. Then naturally, amino acid, unlike carbohydrate, if you can remember, in the case of monosaccharide, we say you must naturally occurring monosaccharide exist in form of D isomers. D isomers. But in the case of amino acid exists naturally in L isomers. They naturally exist in L isomers. So, however, some D isomers can be found naturally in some mammalian tissues and some bacteria. Sorry, time is missing, but let's see how far we can go. So, are you with me, class?
Yes, sir.
Yes, sir.
Okay, now classification of amino acids. How are these amino acids classified? Although when you read a textbook, you will see a different form of classification, but basically they are trying to do the same thing in a different way. So when you read, you will see the explanation given is the same will be given here. And let's see how these amino acids were classified. The 20 amino acids were classified on the basis of their structure. They are also classified on the basis of structure. They were classified into 7. And we'll see. You have amino acids that have an aliphatic side chain. We have amino acids that have an aromatic side chain. We have an amino acid that contain a hydroxyl group. We have amino acid that contain a sulfur. We have acid amino acids, and they are amides. We have basic amino acids, and then we have an amino acid, which we will see. Because based on the course outline of this course, we'll see the classification on the basis of structure. It's much more relevant to the context of this course. Then there is also another classification based on polarity. This classification identifies amino acids that are polar or partially polar. And of course, we have seen that we will see that this amino acid, there are those containing charges, those containing that doesn't contain charges. Although basically all of them have the charges, that we will see how others differ from others on the basis of the nature of their side chain or the alcohol. And there are also division or classification on the basis of nutritional requirement. They were classified into essential. Some of them are essential. Why are they essential? Because the system cannot synthesize it. The biological system cannot synthesize it. So even amino acid cannot be synthesized by you. That amino acid is regarded as essential amino acid. So you can only get that amino acid when you eat food. From the diet you eat, then you obtain that amino acid. So if you are not eating a food that contains this amino acid, you will have deficiency in that amino acid. So one of the reasons why nutrition is always recommended people eating the balanced diet that contain all those things needed in just what you are lacking, so you get it. We have non-essential, and the non-essential, for example, the essential include arginine, histidine, valine, leucine, isoleucine, methionine, phenylalanine, threonine, tryptophan, lysine. So we'll see each and every one of these ones in terms of the name amino acids. And we have non-essential that the body can produce, like glycine, alanine, serine, cysteine, asparagine, aspartate, glutamate, tyrosine, proline. So although we have also what we call semi-essential, why they call semi-essential? Because they are produced in less quantity or less than the requirement. So even when they produce, they don't meet up with the requirement, that the requirement. This includes histidine, arginine, lysine, and methionine, which we initially we mentioned them as essential amino acid. So amino acids were also classified on the basis of their metabolic change. What happened in the system? Remember, we've known that amino acid, when you eat a food that contains a protein, the body needs the protein. It uses it for whatever they need it for. But once the body uses, taking what it requires, then the excess is not needed in the body. Therefore, the body needs to metabolize it, need to change it to something else. So that it can, at least maybe to carbohydrate, if the carbohydrate is needed, then the carbohydrate can be stored, or it is converted to fatty acids. The fatty acid can be stored in the body for future use. But amino acids are not stored for future use. Therefore, it has to be broken down. So what are the pathway? What is the point of this metabolically? So it can, amino acid, all the 20 amino acid can either be glucogenic. Glucogenic in the sense that amino acid can be broken down to produce or can be metabolized to produce glucose, or ketogenic to produce a fatty acid or a ketone body. Somebody start this. Is somebody talking?
I can hear you, sir. Yes, I can hear you, sir. I can hear you now, sir.
Okay. So it can either be used for the synthesis of glucose or the synthesis of fatty acid or ketone bodies. We all know what is a glucose. We all know what is fatty acids. Then ketone bodies also, I want to believe in metabolism. We also know what ketone bodies, but they are more related to a compound that are more closely associated with fatty acids. And then we have both, where they can either be used for glucose or for the synthesis of fatty acids or ketone bodies. Is that clear? Do we have the basis of this classification?
Yes, sir.
Yes, sir.
Good. So we are going to, like I said, on the basis of, based on the requirement of this class, we are going to discuss.
Excuse me, sir.
Yes, Ms. Ola.
I need to draw you back, sir. That polarity, the polar and non-polar is not that clear to me. But I didn't want to just cut you short when you were talking about it.
Okay. The polarity here, the amino acid, the 20 amino acids were divided into two: polar and non-polar. So the polarity, more or less, when you look, what make an amino acid or a molecule to be polar or non-polar? I think when you go back to our previous class where we talked about water and properties, you can from there even get a lot of information where we talked about formation of dipole or partial charges. So if a partial charge can make substance to dissolve in water, what of a charged molecule? Of course, a charged molecule will have a high chance to dissolve in water than the partially charged molecule. So the issue of polarity with regard to amino acid, basically it is more when you look at it from the nature of the R group. Because some R group may look polar, some are non-polar. But when you look at the common group we mentioned, which is the amino carboxyl and the hydrogen attached to the alpha carbon, we'll see that in solution, this group can become ionized, and as such, once they are ionized, they can be soluble. So the issue of polarity now has to do with to what extent all of them can be regarded as polar. All of them can be regarded as polar, but some are more polar than others. So the degree of polarity is not enough. The ones that are highly polar and the ones that are partially or less polar. Are we together? Did you
Yes,
get
sir.
it?
Yes, sir.
Yes. So the classification is on the basis of that. Not completely non-polar. When we say completely non-polar, it doesn't dissolve. But to some extent, why do we even say this classification is just the degree of, refer to the degree of polarity? Because when you look at it, even from the explanation we get in the last class, yes, you will be told that oil, fatty acid do not dissolve in water. But in the previous class, we made mention of some part of fatty acid that can dissolve in water. So they interact with water. Yes, you can say overall is non-polar, but of course there is the degree of level of interaction, polarity that happens even within the what we see as non-polar like oil. Is that clear? So is the degree of polarity. So now let's look at the classification on the basis of structure.